Hi, we are METU ROVER from Middle East Technical University, Ankara, Turkey. And this is our first year in URC with our first rover, Improviser.
To obtain lightweight and robust rover, square-shaped carbon fiber profiles are used on chassis. Connection points and bearing mounts of the chassis are supported with aluminum nodes. In addition to compact chassis design, wide wheel spacing is adjusted to provide more secure drive on the terrain and prevent possible tipping. Rocker suspension system and non-pneumatic polyurethane tires are designed for a smooth ride. Differential motion between two rockers is provided by a differential bar with minimal backlash. Locomotion motors are placed into aluminum wheels to prevent any collision with motors on terrain. Reaction forces and moments on the motor seat are eliminated by using double bearing support. The robotic arm of our rover has 5 degrees of freedom with an end adapter. The kinematical design of the arm is carefully tailored to have maximum functionality and ease of use on different URC missions. The shoulder elevation and wrist pitch axis of our arm is actuated via a worm gear mechanism to have a self-locking feature preventing backdrive like on our linear actuator. The shoulder azimuth axis is driven by a stepper motor and spur gears. The wrist roll, which has unlimited turn capability, is actuated through a gear train of considerable inertia that practically prevents the backdrive as well. The whole system is designed to lift 6 kg of load and successfully tested.
Joints of the robotic arm will be teleoperated to the desired configuration using manual joystick control. Movement motion planning library will be used to solve for inverse kinematics and plan a collision-free path through the environment. Our control unit has also been designed to ensure the modularity of robotic arm system and is directly connected to a rover control unit. Wireless communication will be facilitated over 204 GHz Wi-Fi network with ubiquitous Ballot M2 booster for better long-distance performance. Custom communication protocol has also been designed to reduce data transfer between the rover subsystems and ground station. As a backup, a LoRa radio module will also be used to send mission-critical data or reset the whole system in case of issues related to the main Wi-Fi system happens. To keep system complexity at a minimum, multiple PCBs have been designed for each system. At the heart of our hardware architecture lies a rover control called RCU, acting as a gateway connecting different subsystems with each other. Additionally, a custom motor control unit capable of controlling both position and velocity has been designed. The rover will be powered by custom-built 24-volt battery pack with an 8P arrangement managed by BMS called Battery Management System. An E-stop button is placed on the chassis to be able to quickly respond in a case of emergency.
Robot operating system runs all drivers of peripherals like radars and sensors, as well as all applications to execute URC tasks. Z2 camera is placed on the front side of the rover and it supplies a stereo video stream. Moreover, Z2 Wrapper library publishes the stream as a ROS message for the use of localization, navigation, detection, and mapping applications. RTOP map is used to generate point cloud maps to be used in the autonomy of the rover's navigation. Similar to the panel used in the competition, a replica of it was made and used for the training of the machine learning model. The operator on the base station will receive the stream augmented with the prediction of the model on board. We developed an algorithm to detect the posts and gates and publish the relative location of each leg to go through the gate, which is essential to complete the autonomous navigation task. ROS-based navigation stack called MoveBase is used for the locomotion of the rover. A state machine leads the rover to start any navigation legs, inform the operator after ARTIC detection, and traverse back to the initial point once all legs have been reached. We created a custom GUI with Python in order to visualize and examine the science data. Graphical user interface also monitors the rover and the robotic arm on operation. It informs the team about the condition of the rover and helps the operator for better control.
Science team aims to use an interdisciplinary approach, conducting astrobiological, geological, and atmospheric research. Before any assessment is carried out, contamination is minimized with sterilization of the end effector and separate sampling funnels for different sites. The geological assessment starts with measuring the soil sample's temperature, relative humidity, weight, and density. Soil density is measured with the pycnometer the team is designing. Meanwhile, a CNN algorithm developed by the team is used to detect minerals in rocks. The database created for the CNN algorithm is also used to filter out certain properties such as water presence. Mineral composition in rocks and soil are investigated using a 532 nanometer Raman spectrometer. Raman is also used to detect biosignatures such as amino acids and beta-carotene. As a means to gather data about the biological activity, two colorimetric assays which are for peptide bonds and polysaccharides are used. A luminescence assay is utilized to differentiate extant from extinct life. Atmospheric data is acquired continuously with various sensors such as UV light, dust, temperature and humidity. Microscopy will be used in order to check for gross morphological structure and grain size of rocks. Finally, to investigate the site holistically, a Markov decision process solution algorithm will be utilized.